In our last class, we discussed the operating principle of two different types of ADC. One was the flash analog to digital converter, another was the successive approximation analog to digital converter. In today's class, I am going to introduce two other type of ADCs. One is called the single slope ADC, another one is dual slope ADC. So first of all, let me discuss the working principle of the single slope ADC. Now, in terms of the block diagram, the different components that is supposed to be present in a single slope ADC that is represented here in terms of a block diagram. So in the single slope ADC, we are again going to have an op-amp which is going to work as a comparator. And this op-amp is going to compare the input analog voltage Vin. So this would be the analog input voltage after passing it through a sample and hold circuit. So for a particular duration, we can consider that this analog input voltage is going to be a constant voltage being supplied to the non-inverting terminal. Now this voltage is going to be considered compared with the voltage which is generated by this ramp generator. So we can denote it as VR over here. With respect to the comparison between these two voltages, the comparator signal will either be high, the output of the comparator will either be high or low. Depending upon that, this clock pulse will be supplied to the counter and the counter will start counting. So this could be a type of decade counter. So different types of counter you have studied in your digital logic course. So a particular type of counter can be used to increase the count whenever it receives a clock pulse, and depending upon how the number of counts done for a particular duration, that particular representation of the output of the counter after a certain amount of count, that will be a representation or equivalent representation of the analog input voltage Vin. Now about the working principle or how long the counter will count, I will try to explain a little bit more later on. Now there would also be a control logic circuit that will actually send some controlling signals to the counter, the RAM generator, or the latches. So the latches are temporary storage used for temporarily storing the values that is generated by the counter after a count for a particular input voltage is over. So before going to the operating principle, let me discuss a little bit more on the ramp generator. The ramp generator is actually going to generate a straight line with a constant slope depending upon a particular reference voltage that is supplied at its input. So we can use this sort of a circuit using op-amp in order to generate the ramp signal. Now you're supposed to study this sort of a configuration of op-amp. So do you remember what this sort of configuration is called? What type of circuit is this one?
So negative feedback.
Well, negative feedback, but when you have a capacitor in the feedback path, then that particular circuit signifies a special type of application.
So differentiator or integrator?
Well, it's actually an integrator. If it is if it was a resistor in the feedback path, then you could have said that okay, it is inverting amplifier, but when you place a capacitor, it is supposed to work as an integrator, and in the reverse way around, it will work as a supposed to work as a differentiator. So this integrating circuit, when there is a constant reference voltage, suppose that is input, and the output side, it is going to give a straight line. Now, as we have denoted the ramp generator output as VR over here, let me denote the output of the integrator as VR here as well. So in general, for an integrator circuit, the output voltage is defined through this equation. So suppose from 0 to a particular time interval, the reference voltage is integrated. So this is the general expression for the output of an integrator using op-amp. Now, for this case, we are considering a constant reference voltage, and we want to generate a straight line that will have a positive slope. So in order to obtain a positive slope, we are going to provide the reference voltage to be we are going to supply a negative voltage as the reference. So if we supply a negative voltage as our reference, this negative term and this negative term is going to nullify each other, and integrating from the limit to 0 to t, so 0 to t dt, you can easily suggest that you will have this sort of an expression for the output of the ramp generator. So this is nothing but an equation of a straight line, and this is going to be the slope of that particular straight line. So if we have time along x-axis and we plot the voltage VR along the y-axis, so with the increase in time duration, we are supposed to have a straight line with the slope V referenced by RC. So this is the signal that is actually getting compared with the input analog voltage. Now, the input analog voltage is supposed to be held constant for a particular time. So suppose this black line is representing that input analog voltage. So what will happen to the comparator output up to this limit? Will it be high or will it be low for this duration? Anyone? For this duration, your input voltage is greater than the ramp voltage, or the ramp voltage is greater than the input voltage?
So input voltage is greater than the ramp.
So if input voltage is greater than the ramp voltage for this period of time, what would be the comparator output? Will it provide a high signal or a low signal?
Sir, it should be low signal.
Why it should be low signal? I mean, I have been repeating this for the last in the discussion of the last two ADCs as well, that when you have an op-amp which is working as a comparator, when the voltage at the non-inverting terminal is greater than the voltage at the inverting terminal, it sends a high signal as its output. So here, as the input voltage is greater than the ramp voltage for this period of time, the comparator is supposed to send a high signal for this entire duration as well. If the comparator output is high, the AND gate is getting a 1 at its one of its terminals. So at the other terminal, if the AND gate is having a clock pulse, so what will happen to the output of the AND gate?
Output will be same as the clock pulse.
Yes, so you can say that our output will follow the clock pulse. So for this entire duration, the clock pulse is going to be supplied to the counter. So upon receiving each clock pulse, each period of a clock pulse, the counter will increase its count by 1. In this way, the counter will continue counting for this duration of time. And at the end of this duration, suppose at this point, when your ramp voltage is equal to the comparator voltage, input voltage, the comparator is going to send a low signal. If the comparator is sending a low signal, then the AND gate is not supposed to pass the clock pulses towards the counter anymore. So as much as the counter has counted before the clock pulse is removed, that is actually the digital representation of the input analog signal. So graphically, it is again represented over here. So this straight line is representing the ramp signal, and this constant line is representing the input voltage. So before the ramp signal is equal to the input voltage, the comparator output is high, and as the comparator output is high, the AND gate is passing the clock pulses towards the counter, and the counter is increasing its count upon receiving each pulse. So at this point, when the comparator is providing, the ramp signal is becoming equal to the input voltage, then the comparator is going to send the low signal. So as one of the terminals of the AND gate is getting a low signal, the clock pulse is not going to continue to flow towards the decade counter. That's why the counting process will stop, and as much as the counter has counted up to this point, that would be the digital representation of the input analog signal. So beyond this point, the comparator output is having a transition for certain amount of time, and the counter is also stopping. The clock pulse is also stopped to be passed to the counter. So when there is a transition, when this control logic circuit detects that there has been a transition from high to low, the control logic circuit sends an enable signal to the latches, which are used to temporarily store the counted value before another count is completed for another set of input voltage. And after a certain small duration, suppose t2, the control logic circuit is also going to send two other signals. One is towards the counter and one is towards the ramp generator, to reset both the counter and the ramp generator, so that the ramp generator starts generating a signal starting from 0 again with a constant slope, and the counter is reset to 0 so that it can again start a new count. And by that time, the analog input voltage, which was held constant for a small duration of time by the sample and hold circuit, that is supposed to change by that time as well. So at this particular point, after t1 duration, so at t1, t equals t1, we can write the output of the ramp generator to be equal to V reference by RC into T1. So we are just replacing T with T1 over here. So after we do that, at this point, we know that this particular voltage, ramp voltage, is actually equal to the input voltage. So from here we can also write an expression for T1, that is V in by V reference into RC. So for a particular arrangement, RC, the values of resistor, capacitor, and the reference voltage is supposed to be constant. If these three values are constant, then we can say that T1 will be directly proportional to the input voltage. So if T1 is directly proportional to the input voltage, and also T1 is the duration, it is the duration for which the counter is increasing its count. So we can say that whatever the counter has counted within this period of time, that should be also a representation of the input voltage then. So in this way, actually the single slope ADC operates. So with the input voltage is actually made or approximated in terms of the time period during which the counter is operating. Okay, now for this particular type of ADC, the single slope ADC, one of the drawbacks is that, suppose for ideal scenario, we are considering that the values of R and C is going to be constant. The value of the reference voltage is supposed to be constant as well. So we can say that the conversion time T1 is directly proportional to the input voltage, or they are directly related. Proportionally related. However, you know that the values of resistance and capacitance may vary depending upon the surrounding environment, or depending upon some variation in some parameters in the surrounding environment. For example, the significant change in resistance uh, can be there if there is too much variation in the temperature in the surrounding environment. So if any one of these quantities are varying, then it cannot be said that T1 is directly proportional to the input voltage. So in that case, the approximation of the input voltage will be a little bit less accurate, because the effects of variation of R and C will also play a significant role. So to eliminate this particular drawback, the dual slope ADC is was actually introduced, so that from the calculation of the time, the effect of R and C can be eliminated. Now, before I move on to the dual slope ADC, let me just say that this time duration T1 can be also referred to the total conversion time, in this case for single slope ADC. So this is the time required for the ADC to complete the conversion process. So this can be also referred to as total conversion time. And in terms of the time period of the clock pulse, if the time period of the clock pulse is represented by CLK or T clock, then it can be also expressed as like this: n multiplied by the time period of the clock, where this small n is representing the number of counts done by the counter. Now moving on to the dual slope ADC. Okay, regarding single slope ADC, do you have any question? Okay, no response. Then
Sir,
yeah.
Why is it that this single slope analog to digital convert? I'm comparing it with the last lectures. I've seen that in the last lectures we have DAC that does the conversion. So here, instead of the DAC, the RAM generator is being used. Is it that this RAM generator is replacing the DAC in this circuit here? Oh.
No, the two are completely different. I mean, the operating principle of the two ADCs are completely different. That is using a different type of register, successive approximation register, to convert the output of the successive approximation register. So the successive approximation register is providing an output in terms of binary digits or binary bit sequence. So that bit sequence has to be converted somehow. That's why the digital to analog converter is necessary over there. But here we don't need a separate digital to analog converter, because we are not using any particular register that is giving us its output as in binary form, because the ramp generator itself is giving you an analog signal. So you can use that analog signal, or I mean compare that analog signal directly with the input analog signal. So that's why it is not necessary for you to use a DSC over here, because there is no necessity of conversion from binary bit sequence to analog voltage. The ramp generator itself is going to provide you an analog signal that is being compared with the input.
Yeah, thank you very much, sir. That's my point.
Now, in case of dual slope ADC, similarly, first of all, a block diagram is representing the necessary elements for completing the conversion process. For this case, in case of single slope ADC, you have seen that the integrator is integrating only one reference voltage. I mean the reference voltage only for a particular duration to generate a single straight line with a constant slope. Now from the name dual slope, you can easily suggest that then in case of dual slope, maybe we are going to have two straight lines with two constant slopes. So that is going to happen in case of dual slope ADC, and the integrator or the ramp generator, we can say, it will integrate two different voltages, and due to two different integration process, or I mean the integration process is going to take place for two different times instances. Two different straight lines will be produced depending upon the magnitude of the two different voltages. So one voltage that is going to be integrated first is the input analog voltage, and the negative magnitude of the input analog voltage is taken in this case, and the other voltage that the integrator is going to integrate to generate a straight line is the reference voltage. Now whatever the output that is being generated from the integrator, it is denoted over here as VB. So that output voltage of the integrator is going to be compared using a comparator, where the non-inverting terminal of the comparator is connected at zero potential. So the voltage is actually going to be compared with zero potential. So this comparator is actually in a sense going to work as a zero level detector. And based on the comparator output, there will be a control logic circuit here as well, which is actually going to govern the entire process. Now this control logic circuit is actually responsible for passing the clock pulses towards the counter. It is also supposed to detect any overflow in the counting process. If the counter has counted up to its maximum limit, then the counter is supposed to send an overflow signal to the control logic. Actually, this arrowhead should be on the reverse direction. So if the counter has counted up to its maximum limit, then the counter is supposed to provide an overflow signal to the control logic circuit. And whenever the control logic circuit receives this overflow signal from the counter, the circuit will send an actuating signal to change the position of the switch, and the switch will be location of the switch will be switched towards the V reference, and the reference voltage will then be getting integrated for the next cycle. Now, to elaborate a little bit more about the operating principle, so like I said, that the circuit will start its operation by integrating the input voltage first. But how long the input voltage is going to be integrated? It is going to be integrated until the counter has finished counting up to its maximum limit once. So the input voltage will be integrated So the input voltage will be integrated up to the maximum limit of the counter, or for a duration that is necessary to reach the maximum limit of the counter. Okay, then I should write it like this. For a duration to reach the maximum limit of the counter. So when the counter reaches its maximum limit, suppose if it is a 3-bit counter, then the counter is supposed to start from 0, 0, 0, and its maximum limit is up to 1, 1, 1. So upon receiving each clock pulse, the counter is going to raise its count by 1, and it will reach up to its maximum limit of 1, 1, 1. So after reaching the maximum limit, if the counter receives another pulse, then it will send an overflow signal, and it will reset its values back to 0, 0, 0 again. So up to this point, when the counter reaches its maximum limit, the input voltage is going to be integrated. Now, moving on into the next slide, let's say T1 is the duration that is necessary for the counter to count up to its maximum limit. So if it is an n-bit counter, the maximum limit for the maximum number of counts done by the counter should be 2 to the power n. And if the time period of the clock pulse is represented by TCLK, then the total duration to reach this maximum number of counts will be 2 to the power n multiplied by T clock. So that will be equal to T1. So for this duration of time, the input voltage is going to be integrated. So in terms of the equation of the output voltage of the integrator, we can write suppose at T equals T1, the output voltage of the integrator, suppose VB1, due to the input voltage will be minus 1 by RC 0 to T1 minus V in into dt. So ultimately, this would be our contribution to the output of the integrator due to the input voltage up to T1. Now at T1, the counter has counted up to its maximum limit, so a overflow signal will be sent to the control logic circuit. So the control logic circuit will actuate a signal to control the switch, and the position of the switch will be towards the V reference now. So from T1 to T1 plus T2, the reference voltage is going to be getting integrated. So the component of the output voltage of the integrator VB2 due to the reference voltage can be now written in similar fashion. So T1 to T1 plus T2 V reference into dt. So in this case we are going to have a negative slope, and as we are considering these two time intervals, ultimately we are going to be left off with T2. So for the first case you can see the slope is positive, for the second case you can see the slope is negative. That is indicated over here as well. So up to T1 the input voltage is getting integrated with a constant slope, positive constant slope, and from T1 to T1 plus T2 the reference voltage is getting integrated with a negative slope. Now for this entire duration from 0 up to T1 plus T2, you can see that the output of the integrator is always positive. So as the output of the integrator is positive for this duration of time, so the voltage at the inverting terminal is now greater than the voltage at the non-inverting terminal. So the comparator is going to send a zero signal, and as long as the control logic unit is getting a zero signal or a low signal from the comparator, it's going to pass the clock pulses towards the n-bit counter. When it reaches this point T1 plus T2, the value of VB is equal to 0, and beyond that the value of VB is supposed to be negative. So at that point, at this point and below this point or beyond this point, the comparator output is supposed to be high. When the comparator output is high, the control logic circuit is going to stop supplying the clock pulse towards the n-bit counter, and the counter is going to be stopping the counting process. So up to T1, the counter has counted up to its maximum limit. So it has done 2 to the power n number of counts. Then it is getting reset to 0, 0, 0 again, suppose whatever the number of bits. Then for T2 duration of time, it continues its count again. So the number of counts that it has done for this duration of T2, that is going to be a representative of the input analog voltage. Now how can that be justified? So we can further examine these relationships of the integrator output voltages and show that the input voltage is actually getting proportional to this duration of T2. So from that it can be considered that the counting done by the counter for this period of time would be a representative of the input voltage. So for that we have considered the two different components of the integrator output, VB1 and VB2. So we can cumulatively write the output of the uh, integrator for the entire duration of time to be VB1 plus VB2, which is V in by RC into T1 minus V reference by RC into T2. Now at T equals T1 plus T2, the integrator output voltage is equals to 0 at this point. So if we set this expression to be equal to 0 at t equals t1, we can easily rewrite it as V in by RC into T1 equals V reference by RC into T2. From both sides, this term RC is going to be cancelled out, and we can write an expression for T2 in terms of the other three parameters. So for this case, the reference voltage for a particular configuration can be considered to be constant, and also for a particular fixed clock pulse, a fixed period of the clock pulse, the time t1, which is actually the time required to count up to the maximum limit of the counter, this is actually constant as well, because the maximum number of counts that an n-bit counter can uh, do is actually fixed. The clock pulse is also fixed, so this term t1 can be also considered to be constant. So here the term or time duration t2 is directly proportional to the input voltage. So the number of counts done during this period of time is actually going to be a representation of the analog input voltage. Suppose for this duration of t2, if the counter counts for small n number of times, so that number of count is actually going to be representative of the input analog voltage, and the binary bit sequence corresponding to that particular number of count is going to be the digital representation of the input analog voltage. Now this particular design is eliminating the effect of R and C from the integrating time duration. So the conversion time that is necessary, that is not supposed to be getting affected by the variation of the values of R and C. But what could be the possible disadvantage of this particular type of circuit compared to the single slope? Any suggestions? Okay, the possible disadvantage is that the overall conversion time is going to be higher compared to the single slope ADC, because in dual slope ADC the integration is done twice. Once the input voltage is integrated, then the reference voltage is integrated. Now the input voltage is also integrated up to the maximum limit of the counter, and after that the reference voltage is integrated for a particular duration of time that is actually representing the that is actually representative of the analog input, but the total conversion time is actually the summation of the two. So the overall conversion time is supposed to be increasing compared to the single slope ADC. But in case of dual slope ADC, as the effects of R and C is eliminated from the conversion duration of the conversion, the data obtained is supposed to be more accurate compared to the single slope ADC. The expression for total conversion time if we represent the total conversion time by capital T, it would be T1 plus T2. And T2 can be represented in terms of T1 as V in by V reference into T1, and eventually it can be written as T1 into 1 plus V in by V reference. Another way to represent the conversion time, total conversion time, capital T, is to represent in terms of the time period of the clock pulse. So for T1, the representation of T1 in terms of the period of the clock pulse that has been already mentioned in the previous slide, one of the previous slide, that is 2 to the power n multiplied by T clock plus T2 can be represented as n into T clock. So n is the number of counts done during this duration of T2, and this would be the overall conversion time for the ADC. Now both the single slope ADC and the dual slope ADC is working in a principle that their conversion process is a bit slower. So for applications which requires faster response or faster conversion, such as data acquisition or signal conditioning or signal processing, so this type of ADCs are, the use of this type of ADCs is not that much useful. But in case of applications which require better accuracy, or where the priority is to obtain a more accurate result, this dual slope ADC can be a very useful choice and an economic choice. For example, for the digital voltmeters or multimeters, or different digital weighting scales, for those type of applications, the dual slope ADC can be used to convert the analog data into digital form. Now, for this class, I wanted to discuss up to this dual slope ADC. Now, I don't know how much you have understood, because there were very minimal response. And if you have any question, you can ask, or I would like to end today's session.
There is no question.
Okay, if there is no question, then that is it for today. You guys should try to go through the discussion of today's class. In the next class, I'll try to discuss one example regarding the single slope ADC. So by this time, try to go through the theoretical part, and after going through the example in the next class, I'll try to discuss two types of DSC, and that will conclude our discussion on data converters.
Okay, sir.